Hi, I'm Craig Schurstan, a PhD student from the University of Alberta, and today I'm presenting a preliminary investigation titled Work in Progress, Temporally Extended Auxiliary Tasks. This is work that was done while I was an intern at Borealis AI, where I had the pleasure of working with my colleagues Bilal Kartal, Pablo Hernandez-Leal, and Matt Taylor. This work considers the deep reinforcement learning setting and investigates the impact that auxiliary tasks can have on representation learning, as measured by an agent's performance. For the purposes of this talk, I define an auxiliary task as any loss hanging off of a shared core representation network whose only job is to provide gradient for training that core representation network. This is in contrast to the primary tasks, the policy and value estimate, which might be used for actually learning the policy then. Here we consider a specific type of auxiliary task, one that is predictive and takes the form of a general value function, or GVF. A GVF is simply our usual value function definition, the expected discounted return, but instead of summing future rewards, we're going to sum over some other signal, C, which we refer to as the cumulant. The cumulant can be any measurable signal available to the agent. In recent years, numerous papers have shown that various auxiliary tasks can improve policy performance. However, it is not well understood what sorts of tasks help or why. Here we set out to explore one simple question. What effect does the auxiliary prediction timescale gamma have on performance? Our hypothesis is that auxiliary tasks which are predictive, that is, they have a gamma greater than 0, will outperform those which are simply reconstructive or have a gamma of 0. Further, we expect that as gamma increases towards the discount used by that of the policy, that performance will continue to improve. The reason we hypothesize this is that in the on-policy setting, auxiliary tasks with similar timescales as the policy should have similar or even the same feature dependencies as the policy itself. This is an assumption we make. In the sparse reward setting, this should help the representation network arrive at similar features faster. For our experiments, we use an auxiliary task, which we refer to as a TD autoencoder, or TDAE, which uses the input image as the cumulant of our GVF. The reason for choosing such an auxiliary task is that autoencoders are a common choice for auxiliary tasks. With our definition, we can recover an autoencoder by simply setting gamma equal to 0, and when gamma is greater than 0, we have a collection of GVFs in which the prediction of each pixel is itself a GVF. In our experiments, we use the A2C algorithm on the VizDoom environment. In A2C, multiple agents operate simultaneously on different copies of the environment using the same policy. Each agent collects a trajectory of transitions of length tau. All trajectories are then stacked together to form the training batch. After a training step, the new policy is passed to each agent and the process continues. We considered 3 VizDoom scenarios which were selected because they required memory of the past. The default tau, or trajectory length, used in our experiments was 128 transitions. And we show the performance at this setting of this as the black line shown here. And what we found was that as we reduced tau, that trajectory length, performance suffered. It got worse and worse until we stopped at about at tau equals 8, and this is shown by this yellow line down here, at which point the agent really isn't able to learn the policy. And we use that setting then for the rest of our experiments where we add in that auxiliary tasks. In these plots, our baseline with tau equals 128 is shown as the black line, and with tau equals 8 is shown as the yellow line. We found that when using tau equals 8, adding the TDAE restored performance and even surpassed it at times. In the K item 2 environment, we see that when gamma was 0.5, this orange line, we got the best performance, followed by gamma 0.9, shown in the green, and then the autoencoder shown here as blue. Okay. For Labyrinth, all the TDAEs restored performance, but we don't really see any clear winner. And for 2 color 5, we see that a gamma of 0.9 produced the best performance overall. To conclude, I will summarize our findings. With respect to our original hypothesis, we found no clear relationship between the auxiliary task timescale and performance. This requires more investigation still. We did observe that in some cases, when it was predictive, when gamma was greater than 0, we did see better performance than when gamma was equal to 0. And an interesting observation is that these auxiliary tasks allowed us to reduce the trajectory length, tau, which supports other claims which have shown that auxiliary tasks can make learning less sensitive to metaparameter settings. Thank you for listening. You can find our paper on arXiv where we present additional experiments and results. Thank you very much.